So Elise last week gave you an introduction to the idea of dark energy and the expanding universe. And I think she kind of covered it from more of a theoretical perspective, describing what we think dark energy might be. And then today I'm going to talk more about dark energy from the experimental perspective. So I happen to work on a project called the Dark Energy Survey. It's one of the major initiatives here at the University of Chicago. There's several dozen people here who work on this. And I'm going to focus on that experiment as just an example, because this is a really enormous topic. So I'm going to focus on one particular experiment to kind of give a sense for the activities that are happening in this field right now. So first, let me just do a quick review of dark energy. So Elise told you last week that dark energy, we really don't know what it is. At least right now, it's just kind of a placeholder name for something that's causing the universe to expand. Right? So
to accelerate, right?
To accelerate, exactly, right? So what we can do is that we can make a graph, right, where we take time in billions of years. I'm going to grab the pages pointer real quick. So we have time in billions of years, right? And then this is today, right? And then on the vertical axis, we have the rate of expansion, okay? So what's happened is that over the course of cosmic history, the rate of expansion has always been positive. The universe has always been growing in size, but the rate that it's been growing has been changing. In particular, in the beginning, galaxies were moving apart quite rapidly, but this rate of expansion was slowing down. And then, about 7 billion years ago, something changed, where instead of this rate of expansion slowing down, it actually began to accelerate, this upward turn here. And so one of the major questions is, why did this happen? Right? And this is the fundamental question of dark energy. And then also, what's going to happen next? What's going to happen in the future? Is this accelerated expansion going to continue, or are we going to have some other kind of behavior? So one way to think about this in terms of space is expanding, and this is a point that I think is a little bit subtle. It's confusing for many people. So we're in a universe full of galaxies, right? And so each one of these dots here is representing a galaxy. The color doesn't have any particular meaning. I'm just putting the color so that you can readily identify the different galaxies, right? So let's pick a particular galaxy, right? So let's imagine that we're the Milky Way on this red galaxy here, okay? Now, if you can imagine, at some later time, the universe will have grown. So what we can do is we can just expand space about that point. And that's what's shown here. So I overlaid a second, it's an exact copy of the first image of these galaxies, that first map, where I've just expanded the scale by 5%, right? So this is, from the perspective of this galaxy, right? But what we can do is just shift the perspective to other galaxies, right? So let's shift the perspective to this white galaxy. Or perhaps let's shift it over to this orange galaxy over here, right? What you notice is that every time you shift, what happens is that the galaxies that are near to the galaxy that we're using as our reference point, right? They seem to have shifted a little bit between these two time slices. But galaxies further away have shifted much more. Right? You see this pattern? So what would this actually look like if you were an observer on one of these galaxies? You could make a graph like this, where you say, here's the distance to other galaxies that I see, and the apparent recession speed, how fast they're moving away from you. And what do we think this might look like, based on the plots that, based on these maps that we just looked at, right? Basically, that as objects, as we're looking at galaxies that are further away, they appear to be moving away from us faster, right? And it doesn't matter which galaxy you're sitting on, right? Every observer on every galaxy throughout the universe will see the same pattern, okay? And this is actually what Edwin Hubble became famous for. This is a graph from his original paper in 1929, which I think you may have seen before. But again, pointing out that it's exactly the same figure as what we just saw, where you have distance and the apparent recession speed, how fast the galaxies are moving away from you. Now, this is one part of the expansion of the universe. But what was really shocking and why we're so excited about dark energy is this recent surprise that the rate of expansion is increasing. Not only is the universe continuing to grow, but the rate that it's growing is actually getting faster. And that's what actually makes dark energy distinct from just the normal expansion of the universe. Okay? So one of the things that Einstein told us was that space-time is actually not a passive stage, right? It's actually something that's very dynamic. It actually reacts to the stuff that's in it. And this is actually how Einstein told us to think about gravity. That really what gravity is changing the shape of space-time in a very subtle way, right? And this was pretty mind-blowing. I think even Salvador Dali was pretty shocked by it because he made this painting about 15 years later, showing melting clocks, and this idea that that space-time is actually something that morphs a little bit, right? And it's fairly rigid because gravity isn't actually that strong, but it actually does change shape a little bit. What this means is that if you think about the different types of substances in the universe, they actually have an impact on how the universe is changing over time, its rate of growth, okay? And so two types of substances that we want to talk about are matter, right? So this includes the normal atoms that we're familiar with that make up the periodic table, the stuff that makes up you and me and the Earth and the Sun, etc. But also this dark matter that Tim is going to talk about a lot more in the coming lectures, right? So that's matter. And then this other type of substance is this dark energy, whatever's causing the universe to expand. Now what happens is that if you expand the universe, these two substances behave in very different ways, right? So this matter becomes diluted by the same factor that the volume increases, right? Whereas this dark energy has this very unusual property that its density remains constant. It's not changing. As the universe grows, there's simply more of it. It seems to be somehow like a property of space itself. What this means, oops, I'm going to slide back. Yeah, what this means is that the amount of dark energy in the universe today is actually much larger than it was in the past, right? The universe has grown by 1,000-fold since 13.7 billion years ago. So 13.7 billion years ago, the amount of dark energy was totally negligible. It was such a small sliver of this pie chart of stuff in the universe that you can't even see it, right? But then the universe has grown in size, by this enormous factor, and so the dark energy today is actually the dominant component of the universe, right? It's important to remember that this ratio of the different substances in the universe is actually changing over time. What this also means is that if the universe keeps growing, this dark energy is only going to become more and more important, whereas the other substances will become more and more diluted. It's kind of like a runaway snowball effect. So the real question here is, what is this, right? It doesn't behave like any other substance we know, right? So Michael Turner, he's the director of the Cosmological Institute here, he actually came up with this idea of calling it dark energy, right? And again, it's just this placeholder name. We really don't know what it is, but calling it dark energy makes it sound pretty exciting. Einstein had one proposal for what this might be. He actually anticipated this by many decades. When he wrote down his equations for gravity, he actually left in this term that describes the energy of empty space, right? He didn't really, the theory gives us no information on what the value of this might be. It doesn't tell us what this density is or what actually it might be. Just the mathematics of the theory allow it to exist, okay? But it doesn't really tell us what it is. There's also other ideas, a little bit more exotic. Perhaps it's some kind of modification of gravity. Gravity behaves somehow differently on the scale of millions and billions of light years. Or perhaps it's some kind of energy that's actually changing over time. And people call these ideas quintessence. But for one thing, it's sure to mean Swedish gold, right? We've already seen this with the Nobel Prize for this discovery 2 years ago. So, you might look at this and you say, oh, this is fantastic, right? We've discovered this essentially limitless energy source, right? That's everywhere at all times, and there's more and more of it as the universe grows, right? So if you're thinking in the entrepreneurial style, you might say, hey, this is great. This is a great money-making operation, right? Unlimited energy.
No,
right?
it's no good, because if it's abundant and it's everywhere, who could make money out of it?
Right. Well, if you can make the technology
We commit suicide if
it.
that happens.
Right. But the problem is, in addition to this concern, right, is that the density of this is extremely low. Right? If you were to average this amount of dark energy over the whole universe, it amounts to something like 4 protons per cubic meter, right? Which is trillions of times less than just a single droplet of water. Right? I mean, it's just unfathomably small, right? So what this is really telling us is just that the universe is really big. At least for me, this makes me think about the vastness of the universe. Another aspect of this dark energy problem that's really perplexing is if you think about this density, right, there actually is a prediction from particle physics based on all the types of particles that we know flickering in and out of existence. And the problem is that if you take all the particles we know, right, and they're kind of this energy of the vacuum just coming in and out of existence, you would predict a number that's 10 to the power 120 times larger. So just to write that down as the actual numbers of zeros and ones, right? This is a really bad miscalculation, right? This is probably the worst miscalculation in theoretical physics, right? And what this is really telling us is that there's something really important to understand, right? Like we've missed something really big. And this dark energy problem is telling us that we still have a lot more to learn about the basic laws of physics, despite the tremendous progress we've made. Also, there's this question of why do we have this amount of dark energy today? Why is it that the amount of dark energy in the universe is kind of just right so that galaxies could form, right? You kind of have this runaway snowball process where the amount of dark energy is growing with time in the universe, right? And so you might ask, if there had been just a little bit more or a little bit less dark energy in the beginning, right, maybe the appearance of the universe would appear very different than it does today. Right, this is another perplexing question. But I'm optimistic about this because there's lots of young people working on the problem. These are just a selection of people that are, that have been through University of Chicago working on this, and so I think that there's a lot of hope. So I'm going to talk about one of the experimental projects to try to solve this. First, let's talk about telescopes as time machines. Right, so this will be kind of just setting a general size scale of the universe. Okay? The idea here is that light has a universal speed limit. It's really fast. It's 186,000 miles per second. Right? So it's really fast. Maybe if you're this guy, you think you could break it, right? But in general, right, this is the speed limit. What this means is that as you look at something, right, that light has taken time to reach you. Right? So if we look at the sun, we're seeing the sun as it was 8.5 minutes ago. Right? And you can extend this idea to say, okay, let's look at the nearest stars. Right? The nearest star is about 4 light years away, and so we're seeing it as it was 4 years ago. If you look at the center of our Milky Way galaxy, right, like this telescope is doing, you're seeing something that's 25,000 years old. Now, if you look up to the nearest galaxy, the Andromeda galaxy, or M31, you're seeing it as it was 3 million years ago. And if you take this to the scale of the most distant galaxies that we can see, we're seeing these as they were 13 billion years ago. Just as a reminder, right, when we look at this image, I think this is another image that Tim showed on the first day. What we're seeing here is a photo that's covering approximately 1/13 millionth of the full sky. Here's the size of this photo relative to the scale of the moon. Each smudge of light in this photo is a galaxy, right? So if you extrapolate that over the entire sphere of the sky, it implies there's over 100 billion galaxies in the observable universe. Again, the universe is really big. Okay, so telescopes are time machines, right? We're able to look back in time, right, as we look further away. The next critical idea that we're going to need to solve this puzzle is redshift. Okay, and this is where those diffraction gratings are kind of come in handy. So right here, I have a hydrogen discharge tube. Right, so I'm going to turn this on. Right, and what you guys have in your hand is a diffraction grating. Okay, so what you should see if you look at this, right? I'm going to turn down the light so you can see this, all right? Just be temporary. Now, you don't want to look right at it. You actually want to look to the side. Okay, you kind of want to look, look off to the left or the right. So can you guys see these spectral lines? Right? If you look off to the left or to the right.
You see the red.
You probably see the red one. At least for me, I see the red one pretty brightly. I can see the kind of the greenish blue one a little bit less. And then maybe see this third purple one. You guys see that?
Yeah.
Right? Okay. I'm going to go ahead and turn the light on again. Everyone seen it okay?
Yeah.
Okay. So what we're seeing here is that every type of atom has a distinct spectrum of light, right? So what we've done here with this hydrogen discharge tube is that we've energized the atoms, and then they're giving off light, right? And what that spectrograph in your hand did is basically separate that light into its different constituent wavelengths, right? So the reddish is the longest wavelength, and the purple is the shortest, right? And so what's really interesting, though, is that if you look at astronomical objects, right, we see that they have the same pattern of spectral lines as the materials on the Earth, right? We look at the sun, and it's made of hydrogen, right? The same hydrogen that we have on Earth. And we can tell because each type of atom has a specific signature of spectral lines. And so when we look at the sun, we see H alpha, which was that really bright red line that you guys could see through the spectrograph, right? To me, this was must have been incredibly profound when scientists realized this. Because when you look at the sun, it doesn't look anything like the Earth, right? It looks like it would be made out of some fantastic substance, and it's made of the very same stuff that we have on the Earth, okay? What this means is that you can look at a very distant object, right? Something that could be millions or even billions of light years away, and you know that it's going to be made out of the same stuff as on Earth, right? You can look at it and you can try to figure out its chemical composition. So this is an example. This is when people first looked at this object, they thought it was a modestly bright star, okay? It has this little funny thing here that they weren't quite sure what that was, but in general, it looks like just like a modestly bright star. It's something you can see with an amateur telescope, okay? And then what happened is that in 1963, Martin Schmid wrote a paper about this. And what he noticed is that when he looked at the spectrum of this object, right? Here's the spectrum of this object. It's called 3C273. And then here is just a comparison spectrum of a nearby star. What he noticed is that that bright H alpha line that you would expect from hydrogen had disappeared. It had gone to a part that was so red that he couldn't see it with his telescope. And these other hydrogen spectral lines had shifted, right, to slightly longer wavelengths, right? He made a chart showing the factor by which these spectral lines had shifted. He noticed this pattern just with longer wavelengths. And then he has this beautiful paragraph where he describes the implications, right? You can kind of see this ticking in his mind. And what he realizes is that this is a galaxy that has this cosmological redshift. It implies that it has this incredibly high velocity, right? Because what can happen is that, when the ice cream truck goes by, and as it's moving towards or away from you, the pitch changes, right? We call this the Doppler shift, right? Something like that happens as the universe expands. And what he realizes is this incredibly high apparent velocity causing the spectral lines to shift meant that this was an object that was 500 million light years away or more, right? And what that meant is that this object, in order to be as bright as it appears at Earth, had to be at least 100 times brighter than any of the nearby galaxies, right? That this was some incredibly fantastic, bright, luminous object very far away. This is just another way of visualizing what he saw, is that basically you expected those different hydrogen spectral lines to be at these wavelengths, and they actually got shifted to longer wavelengths, right? And so he was the first person to really see these incredibly distant objects. These are now called quasars, by the way. So I thought really long and hard about how to explain this cosmological redshift, and it turns out that I just couldn't think of any way to explain it clearly because all of the analogies that people use, I mean, they have some kind of difficulty. They're not quite right. Okay? It's a little bit subtle what's actually happening. So I really try to avoid equations in talks, but this is the only equation of the talk. Okay? So Z represents this redshift, right? The amount that the light is shifted, right? And as the universe is expanding, what this is telling you is it's a relationship between the size of the universe today versus the size of the universe at the time that that light was emitted, right? In terms of what you would actually observe, what this does is that it changes the apparent wavelength, or equivalently, it changes the apparent frequency. One of the important aspects to note about this is that the increase in wavelength, it actually doesn't depend on how the universe is changing right at the instant the light was emitted or received. All that matters is the total increase in the size of the universe during that time that the light was traveling to you. So just to provide an example, to kind of check our understanding, let's do the test of, suppose we see this H alpha line in a source, right? And we see it at a wavelength of 1300 nanometers when we expected it to be at 656, right? If it had been, this hydrogen discharge tube. So what redshift would that correspond to?
2.
Right. So the wavelength doubled, right? Oh, sorry, this should be Z right here. Yeah, that should be Z. That's a typo. My bad. So the answer is redshift 1, okay? So, and what that means is that at a redshift of 1, the universe was half of its current size, okay? So what we've learned about here, to kind of review the first part of this talk, is that the redshift is telling us something about the relative size of the universe, right, when the light was emitted. And what this distance measurement allows us to do is it's telling us the light travel time, right? So if you combine both the redshift and the distance, you're actually measuring the expansion history of the universe. Does that make sense? Everyone catch that? That, if you're looking further away, it takes longer for the light to propagate to you. And then at the same time, you measure the redshift. And this is telling us by how much the universe has grown. Okay? So what this allows us to do is to actually measure the expansion history. Right? If we look at many different objects at many different distances, we can actually trace out how the universe has grown with time. And this will actually allow us to measure the properties of dark energy. So one of the major implications of this is the cosmic microwave background. Right? So this was discovered in the 1960s. They were using this radio telescope sensitive to microwaves. And what they saw is that, if you imagine, very shortly after the Big Bang, about 400,000 years after the Big Bang, the universe was about 1,000 times smaller, right? And it was full of this glowing plasma, right? The whole universe would have appeared as bright as the surface of the sun, okay? But then what happened is the universe grew, right? It grew by a factor of 1,000, right? And due to this redshifting, all of that light, right, which we would have seen with our eyes, like the whole universe would have looked as bright as the surface of the sun, all that light got shifted to lower frequencies, longer wavelengths, right? So what we actually see today is this radio hum, right? Radio being a much longer wavelength than light that we see with our eyes. Right? So they realized that they were actually seeing this emission from the very early universe. Nowadays, we can make maps of this cosmic microwave background. And what this allows us to do is to see that the universe was actually uniform in density to 1 part in 100,000 in those early times. Right? This will become important later in the talk, which is why I'm mentioning it now. What's really interesting is that those slight over-dense regions, under the influence of gravity, those actually grew to become all of the galaxies that we see today. Right? So every galaxy in the universe grew out of these very, very small perturbations in density of only 1 part in 100,000. And we'll talk more about the cosmic microwave background later, but it's really important because it allows us to know what the universe was like at the beginning, so that now when we look at the universe, we have something to compare it to. So now I'm going to switch and start talking about the dark energy survey. This is the one experiment that I was going to focus on. what this is, it's a new project. This is it's a telescope, and it takes images of the night sky. That's the fundamental idea. This is one particularly beautiful photograph that it's taken. What it's going to do is it's going to map 300 million galaxies over 1/8 of the full sky over 10 billion years of cosmic history. Right? It's probably the most ambitious mapping project that we've ever undertaken as a species. Okay? This is also the first dedicated survey to study dark energy, and it's using 4 distinct and complementary techniques that I'll talk about in the second half of this talk. So where is this located? It's in Chile. What you do to get there is that you fly into Santiago here, and then you fly up to La Serena, which is a small town along the coast, and then you go up into the mountains. This is what it looks like on the mountaintop. It's incredibly dry. It's at high altitude. It's a great place for observing because the air is very still and clear. There's very little water, so you can see directly out into space with very little interference. It's called the CTIO, Chiricahua Inter-American Observatory. This is the dome that houses the telescope. Here's the door, just to give a sense of scale. Here's what it looks like inside. Okay? So the telescope itself, so this blue part is the mount of the telescope. Here is the mirror, right? It's a 4-meter mirror. And then this giant structure held at the end is the camera, right? It's much larger than a person. Here's just another view. So here you can see the mirror a little bit better. You can see the giant camera. So the light comes in, bounces off that mirror, and goes straight to the camera. And again, the mirror is 4 meters across, so it's quite large, which means it can collect a huge amount of light. Just to give a sense, sorry, you had a question?
The diameter of the camera, what it is, because it's in front of the mirror.
Right, yeah, so you can see that here. So this is a color filter that goes in front of the focal plane. And so, yeah, the camera is about the size of a manhole, right? Like, so this is literally how large that focal plane is. And it's completely covered, with CCD chips. Just like in your digital camera, but these are just very, very fancy, expensive CCD chips. In particular, they have this red sensitivity, right? And we just talked about redshift, right? That distant objects, their light gets shifted to longer wavelengths, more red colors. And so having these CCD chips with this enhanced red sensitivity means that this telescope is especially suited for looking at very distant objects that have been highly redshifted. It comes with these 5 different color filters, and that's actually to try to measure this redshift. And I'll talk about that in a few slides. So, go on. This is just one image that this camera takes. So what you can see here is the same pattern of rectangles here on the sky correspond, if we step back one, they correspond to this layout of CCD chips on the focal plane of the camera, right? So what's happening is the light is getting focused onto the camera, and then this is what you would see in one, sort of just one snapshot, right? And then this is the full moon for comparison, right? So you remember that image that we saw with Hubble, right? And it had that, in scale to the moon, right? So the Hubble footprint on the sky is very small, whereas this is actually quite large, which means that Hubble is great for looking very deep, but this telescope is ideal for surveying a huge amount of the sky. That's what makes them different. So this is one, so what you can do is that you can take all those snapshots and you can imagine that you shift the camera very slightly so you fill in those gaps between the chips. You add all the images together and you get something that looks like this. So in this image, I'm going to turn down the lights just so you can see things a little bit more clearly, just briefly. So this is a star in the Milky Way, right? So you get foreground stars, right? This is a relatively nearby galaxy. You can tell it's this large smudge, right? But the vast majority of objects in this image are actually 1 million times fainter than the limit of unaided human vision, right? And that's what really makes this camera special. That's why it has this enormous mirror to collect the light of these very, very faint objects. And if we zoom in, right? This is actually showing a cluster of galaxies, right? Yeah, looks pretty nice. So I'm going to turn up the lights. Okay, so the way that this, what this survey does is that rather than looking at particular objects, what it's doing is just scanning over the sky, right? It's not, pre-selecting objects. It's literally just stepping its footprint across the sky. And so over 5 years and 525 nights, it'll take a photograph every 2 minutes, right? Just scanning over the sky, and eventually it will map 1/8 of the full sphere that we can see. This is the progress of the survey so far. So each of the rows here correspond to a different color filter, right? And this is just showing the map on the sky. The sky is a sphere, right? So it kind of looks like the globe turned inside out, right? So the parts that are in light blue, these were observed during the first year. And then the parts that were in dark blue, these are parts that were observed during the second year, which we're in the middle of the second year now. And then you might be able to see a few red spots. Those correspond to spots that were observed just last night, right? So this is something I downloaded this morning. One of the other features of this survey is that it picks a few selected parts of the sky that it keeps on returning to much more often, right? So each of these rows correspond to a different small patch of the sky. The different colors correspond to the different color filters. And what it does is that it keeps on returning to these same patches of the sky, and it's looking for things that change, right? Objects that get brighter or fainter over time. And that will become important when we talk about supernova. So a really important aspect when we talk about observational astronomy is that every time you look out into the night sky with a different type of light, you learn something different, right? So this is a sort of a collage, a mosaic of our sun, where each different panel corresponds to a different kind of light, shorter and longer wavelengths, right? So what you realize by looking at this is that the information that you can get about an astronomical object is so much more rich than what we can just see if you could look with a single frequency. And the light that we can see with our eyes is actually a very narrow part of the entire electromagnetic spectrum. This also applies for galaxies, right? So if we look at galaxies in the infrared, so like the more red light versus the ultraviolet, more blue light, what you get is actually this much more interesting picture of the galaxy. And in fact, almost all the images that you see, whenever you see beautiful Hubble images, for instance, they're almost always made in this way, essentially taking a black and white photograph through many different color filters and then combining those later, right? And that's how you actually get these really nice color images. So if we take a typical galaxy, right, and we have a fancy spectrograph, right, what you would see is something like this, right? So it's the brightness, right, on the vertical axis, depending on the wavelength. So going from bluer light to redder light, right? And what you can imagine doing is that if you have a bunch of different color filters, what you can do is that as an object becomes further away, it's more highly redshifted, right? And as it becomes more highly redshifted, that spectrum of light gets shifted so that more of the light is collected in the reddish filters. So in this example, the blue curve would correspond to the intrinsic spectrum of this galaxy, right? And each of these gray regions here corresponds to different ranges of the color filters, right? So initially, this object would have appeared very bright in this G filter, right, which is kind of a bluish color, right? But then as you move it to a redshift of 0.4, right, all of a sudden it gets bright in this R filter, which is kind of a red color. And if you move it to a redshift of 0.8, it becomes very bright in I, which is kind of an infrared color. It's a little bit redder than what we can see with our eyes. So what this allows us to do is, even without a full spectrum, we can still actually measure the redshift of an object approximately by looking at the ratio of colors in the different filters. Okay, this is another piece to our story. Measuring distances in an expanding universe, right? So we've talked about how to measure the redshift, right? Now we have to talk about how to measure the distances, okay? So the way to do this, right, is that we want to come up with distance measures that are things that we can actually observe, right? Things that we can look out to the sky and we can measure. And so these correspond to luminosity distances, right? How bright something appears, and angular distances, which correspond to how large they appear. So these two different definitions of the distance, they preserve our intuition that an object that's further away should appear both fainter and smaller, right? What's really interesting is that these two different definitions of distance actually do not entirely match. In a universe that's growing with size, these are actually two distinct meanings of distance, right? They're both valid. It just depends on the quantity that you're trying to measure. This is very different from our intuition, right? This is not something that we usually think about, right? This is something that applies over distances of millions and billions of light years, right? So what happens is that as you increase the redshift, the luminosity distance just continues to grow, whereas the angular distance, how large something appears, is actually, it kind of tapers off, which means an object will appear to become smaller up to a point. And then actually, if we were to continue this graph, you would see that a very distant object would then start to appear bigger, right? Which again is it's very unusual. It doesn't go along with our intuition, but again, it's because the size of the universe is growing. Yeah, did you have a question?
Yes. Wouldn't dark matter bias or distort the redshifting?
No, because the dark matter doesn't interact with light. Yeah, so that's okay. Fortunately, that's not something we have to worry about. Yeah. So, right. So anyhow, there's these two different ways of measuring distances. Now, so what I'm showing here, this is a little bit complex, but on the horizontal axis here is the redshift, right? So again, this is telling us something about the size scale of the universe. And then the vertical axis is the distance, right? In this case, it's the distance by measuring how bright something is. That as it becomes further away, it appears dimmer, okay? So what each of these different colors represent is if you change the amount of dark energy in the universe, okay? So the red corresponds to there being less dark energy in the universe, and blue corresponds to there being more dark energy in the universe. So what this means is that you're actually able to measure the amount of dark energy in the universe, because you can look at an object, you can measure its redshift, and then you can measure its distance, right? And that gives you a point on this plot. And then you look for the line that goes through that point. So what this allows you to do is by measuring redshifts and measuring how bright objects appear, you can measure something about the properties of dark energy. In particular, you can measure how much of it there is. Here's another example. So this is, it's the same type of plot, but now what I'm showing on the vertical axis is the angular distance, how large something appears, right? So in this case, you measure the redshift to an object, and you measure how large it appears. You put a dot on this graph, right? And then you look for the line that goes through that graph, and then by seeing what color that line is, you can figure out, again, what was the amount of dark energy in the universe. Okay, so this is how we actually learn about the dark energy. Here's just one more example. This is, again, the same style of plot, redshift, and then how bright something appears to measure the distance, except for here, now the colors correspond to the effective pressure of dark energy. Basically, how much does dark energy actually kind of push out and kind of force the universe to grow? And again, it's the same pattern where you measure something, you measure a galaxy, its redshift and its distance, you put a dot here, and then you can measure something about the properties of dark energy. This is going to be the whole game plan for how we're going to measure dark energy. So this is important. It is a little bit subtle. Okay, so now we're going to shift to the tests of dark energy. Right, we're getting very close. So I mentioned that this dark energy survey, it's very special because it's the first survey that incorporates these 4 different techniques of measuring dark energy all in a single survey. And what we're going to see is that actually you need all of these different techniques in order to learn about dark energy. Only one of these will give you some information, but it's incomplete information. It's actually the combination of these that's giving you the richest information. So let's talk about type 1a supernova first. So this is the idea that, when you look out, what you see, so this is one photograph taken with the dark energy survey, and then you come back to that same patch of sky, and all of a sudden you see this, this bright point of light, right? And we now know that this is a stellar explosion that momentarily becomes as bright as an entire galaxy. The amount of time that this is bright corresponds to a few weeks, and that's why the dark energy survey selects a few patches of the sky and keeps on returning to those patches, so that you can look for this brightening. Now, I think Elise talked about this. So, again, if you remember those plots that we just looked at, right, where it's the redshift on the horizontal axis, and then the luminosity distance on the vertical axis, this is shown in kind of complex astronomers' units, but just ignore that. It's really just measuring the luminosity distance. Okay? So each one of these points corresponds to a measurement, right, to one of these supernova that went off. And the great thing about the type 1a supernova is that you know how bright they are intrinsically. So how bright they actually appear in your telescope allows you to measure this luminosity distance. And the main point that I want you to take away from this figure is just that we've now looked at hundreds of these supernovae that have gone off. And the black is the model curve, right? So this is a universe that includes dark energy. And what you see is it's just incredible correspondence between the data, the supernova that we observe, and then the model that includes dark energy, right? We've measured hundreds of these supernova, and we see that there's just this very, very nice fit, right? And this is really giving us some confidence that we're on the right track. And this is largely what led to this Nobel Prize being awarded for the dark energy. Okay, so let's talk about another one. In particular, these so-called baryon acoustic oscillations. Okay. What this is, it's a fancy name for sound waves in the early universe. All right? So remember that we talked about this cosmic microwave background and how it's a map of the universe very shortly after the Big Bang. So what's interesting here is that if you look at the speckles, right, in this map, they're kind of on the scale of about a degree. Right? So this whole map is covered with speckles, and these correspond to these very slightly overdense regions, right? The regions where eventually galaxies are going to form, right? Large accumulations of galaxies. So what actually happened in the early universe is that there were these slight overdensities, and what happened is that these caused sound waves to propagate in the early universe. And this is kind of what it looks like. So let's imagine that this is one particular overdensity. So what's going to happen, right, is this sound wave gets emitted, right? It's just a wave in the density that's flowing outward in time, okay? And so that's just if you have one overdense region, right? But more realistically, you have this whole, complex set of many different overdense regions. And so, again, these will all create their own sound waves, and so it creates kind of this complicated pattern. But in a statistical way, we can still measure this. So what we're going to show here, this is going to be an animation. So on the horizontal axis is the radius going outwards from one of these overdensities, right? So what we're going to see is a sound wave that propagates outward. On the vertical axis is the density, okay? So if we turn this on, right, you see this blue and red, that's the outgoing sound wave, okay? And the reason why it's shown in blue and red together is that in the early universe, it was full of this plasma, and the atoms were connected to the light. Basically, the atoms and the light were inseparable. They were trapped together because they were interacting so often. So in the early universe, they were evolving together. They were kind of moving together in the sound wave, propagating outwards. But then, so we'll see when the animation restarts, right? So here's the, let's see if we can get it. Let's go. So here's the sound wave going out, right? And then right about here, you're going to see them separate. So what happened is that the universe cooled down enough such that the atoms and the light could separate from each other, And what this left is that it actually left an overdensity in the amount of matter. Basically, the matter got left behind. And what you can imagine, this is a very sort of artistic rendition, right? So you can imagine that there's these circles on the sky, right, where there was this sound wave propagating out like a ripple on a pond, and then that became frozen when the light and the matter decoupled from each other, right? And so galaxies preferentially form along these circles, right? So effectively what we're looking for is these circles on the sky. And it's not an easy thing to see. You have to look at millions and millions of galaxies to see this. But again, this is real data now, right? So again, this is the separation, the characteristic separation between galaxies, and then the vertical axis is telling us about the density. And the part that got people excited about this plot is this little bump here, right? You see it's a pretty small effect, right? But you do see this kind of remnant of this sound wave that was propagating out in time. And what this corresponds to is a ruler such that we can measure the expansion of the universe. We basically look at the size of these circles. And that allows us to measure distances. So that's the second method. Another method is the galaxy clusters, right? And what these are the largest accumulations of galaxies in the universe. And so the way that we're going to talk about the galaxy clusters is that we look out into the sky and we see these overdensities of galaxies, right? We see that there's sometimes these groupings of 1,000 galaxies all together. And what we can do is that we can go to our computer simulations, and what we can do is that we can just put in the distribution of matter like we expect in the early universe, and then just let gravity evolve. Right? It's very simple. We just let gravity kind of pull on the matter and bringing it together over time. And then we can try to match our computer simulations with the telescope observations. So I'm going to show a movie real quick to illustrate this because it's a little bit easier to see if we do it this way. So let me turn down the lights. So what this is showing, the top panel, let me see. So this is showing the redshift, and this is showing time since the Big Bang. Where you see the regions that are becoming bright, these are the regions that correspond to a high density of matter. So in the regions that are dark, these correspond to areas where there's not very much matter. So over time, what you see is that just under the influence of gravity, the matter begins to clump together into these regions that are sort of bright, yellow and kind of orangish regions. And so the matter is being pulled together, and it's forming these knots and these filaments. And over time, what's going to happen is that the distribution of matter in the universe becomes more and more clumpy, right? So you remember in the beginning of this movie, right, everything was very smooth. Almost everything was this kind of darkish color. And then over time, you have more and more of these regions where huge amounts of matter have accumulated, and these are where galaxies are forming, right? These are where galaxies are today. Yeah. It's really simple physics. It's just gravity. So this is just another way of looking at this. Again here, the regions that are blue correspond to the regions of high density. Each one of these panels represents a different slice of time in the universe, right? So again, this part in the upper left corresponds to the most distant past, right? And then this part in the lower right corresponds to today. So you can see the universe started out being very smooth, and then under the influence of gravity, it's become more and more clumpy, right? So by measuring the amount of clumps in the universe, we're actually able to learn about the dark energy, right? So what this is showing is it's comparing two different simulations. The panel on the left is showing the density of matter in a universe that has only matter, right? And the simulation on the right, this is showing a universe which includes matter and dark energy. right? So the point to take away from this is that if you have matter-only universe, you have many, many more clumps of matter. You have many, many more clusters of galaxies. Whereas if you have dark energy, what this is doing is causing the galaxies to move away from each other more quickly, and so the galaxies basically have less time to find each other and to form clumps of matter. Do you have a question?
No, I would.
Okay, good. Yeah. So again, more dark energy means that you form fewer of these galaxy clusters. So if you go out and you start counting galaxy clusters, you can actually learn about the dark energy. Now there's one more technique. This is the weak gravitational lensing. So this is a huge topic, so I'm only going to touch on it very briefly. The idea here, we talked about how Einstein told us that space-time is actually dynamic. It responds to the stuff that's in it. And part of what this means is that as light is traveling through a region of space-time that has a very large amount of matter, the path of light actually gets distorted, right? It's actually the same thing that happens when light is moving through glass. The way that a lens of glass works is that basically light is traveling slower through glass than it does through air, okay? And by the same kind of analogy, time is ticking by more slowly in regions with a high amount of matter. What gravity does is that it literally makes time tick by a little bit more slowly, and because the light is it's still traveling at the speed of light, but it's propagating at different rates around this overdense region, it causes these distortions. This is a particularly strong example. So you can see all these arcs, all these kind of bluish arcs that kind of wrap around in circles around this central region. These are actually distant galaxies where their images have been distorted by this effect. So where you see all these fuzzy yellow galaxies in the foreground, this corresponds to there being regions of huge matter accumulations. And then these blue are the background galaxies that their images have been distorted. This is just another example. Here's an amazing example of this. Again, this is like a really huge topic, so I'm only going to touch on it briefly. But what you can do is that, so this map is showing the, sort of the distribution of matter in the universe, right? Just in one little patch of sky. And if you look at the way the light is distorted, what it does is that it kind of distorts the images in the patterns that you see indicated by these white sticks. That basically the galaxies get kind of stretched in the direction where the stick is pointed, right? The shapes get a little bit shifted and stretched. And so what we actually see is just this pattern, right? When we look at the galaxies, we see that their shapes are kind of distorted in a statistical way, and then we use that information about the way the images are distorted to learn about the matter distribution. This is probably the most abstract concept that we'll talk about. Okay, so we have these 4 different tests of dark energy, and I mentioned that the real power of this is that we can combine them. So that's what's shown in this plot here. And again, this is the conclusion of the talk. So one of the main points. So what's shown here is that on the on the horizontal axis, this is showing the amount of matter in the universe, and on the vertical axis is the amount of dark energy. And where you see these colored contours, these correspond to regions where with each different way of looking out into the universe, different regions that are allowed out of these 2 values, right? So if you pick a point on this graph, and say it's inside this green region, right? These correspond to the values of the amount of matter and the amount of dark energy in the universe that are allowed by that particular set of data. Okay? So where you see these different colored regions overlap with one another are regions where all the different ways of looking at the data are compatible with each other. And what you see is that any one of these regions, which correspond to a particular experimental technique, they actually correspond to a very large range of values, right? They have these sort of broad, large shapes. But if you take the combination of these different methods, which is shown in this very small central orange region here, that's the intersection of all these different methods, that's a much, much narrower range of these parameters that are allowed by the data. And so it's really combining these different techniques that allow us to learn the most about the dark matter and about the dark energy. So this is just another way of looking at the information. In this case, it's the amount of dark matter in the universe. And then this is the effective pressure of the dark energy on the vertical axis. Again, it's the same idea as on the previous plot, where when you take the intersection of all these different experimental techniques, that's giving you the most information. It's confining you to the part of the values of these two different parameters of the theory that's most narrow, right? Where you're learning the most and you're excluding the most different alternative theories. Okay, so just to summarize, right, to bring it all together, so dark energy is really one of the outstanding scientific mysteries of our generation. Elise talked about that, and I talked about that in the beginning, that we really don't have any single compelling theory that would explain its properties. The amount of it in the universe is very strange. We saw that prediction where we over-predicted by 1 with 120 zeros after it. Right? It has this strange property that the amount of dark energy is such that galaxies can form in the universe today. It's very strange in that way. But ultimately finding out what it is, it's going to take this enormous worldwide effort, right? It's going to take these huge telescopes using all of these different experimental techniques. And as we saw in those, those last slides, you really need the combination of these different methods to get the most information. No single experiment can do this on their own. And so it's really going to take teams of hundreds or even thousands of scientists working all over the world using all different telescopes to solve this problem. So if you guys are familiar with the Higgs boson, this momentous discovery at CERN, it's going to require something like that in terms of the amount of collaboration and teamwork and experimental expertise to figure this out. And finally, I just want to mention that there are many people working at the University of Chicago that are really actively involved in this project. The principal investigator, the leader of this dark energy survey, is a professor here at the University of Chicago. So it's a really great example of sort of global contributions to science as well. So I just want to say thank you for listening. This is a picture of several of the people who made the dark energy survey happen. And then I'll stop and take questions.
Yeah, in some of the explanations and graphs that you have, you mentioned dark energy, but...
Oh, sorry. I just want to say one thing. So please do not take the diffraction gratings with you. These are to be returned if you can. So let me put these in the back. Sorry, I'll answer questions in just a minute, but I'm going to put these in the back so that if you have to leave early, you can drop them off.
I was thinking that's a lot of money because I put this in the science store.
Okay, sorry, I interrupted your question. But
Oh yeah, it was that you didn't mention the dark matter as and why dark matter will be different than dark energy in changing the way that the universe expands.
Exactly. Okay. So that was illustrated here, but I probably went through it kind of fast. So the idea here is that dark matter and also regular atoms, right? These actually don't exert any kind of pressure on the universe. What happens is that as the universe grows in size, their amount of the density of the matter, it just continues to get diluted with the size. And what what causes the universe to change in its scale, what's actually driving this expansion, is the total amount of energy in the universe. And by Einstein's equation, E equals mc squared, right? This is giving us an equivalency between matter and energy. That matter and energy are sort of, just two different ways of looking at the same coin, right? So what's happening is that whereas the amount of matter in the universe is staying the same, right? It's just becoming kind of spread out, just becoming diluted, right? Like as if you had like a chamber full of gas, right? And you expand the chamber, and now the gas atoms are just further apart, right? But the crazy thing about dark energy, which makes it so unlike any other substance, is that its energy density stays the same. So when you expand the universe, right, you just have more energy, right? And so all of a sudden the universe is reacting to this. It's saying, I'm getting bigger and bigger, but the density is staying constant, right? And this is actually what makes the influence of the matter on the expansion of the universe very different than the influence of the dark energy, right? Effectively, it's acting like a negative pressure, like a pressure pushing outward, because there's just more and more energy as the universe grows.
Thank you.
Yeah.
Is there any thought to the quantization of dark energy?
Oh, like we could somehow measure
Would
its...
that be related to quantization of space-time itself? Or?
Yeah. So I'm not an expert on this. I'm much more focused on the telescope observations. I'm actually going to go down to Chile to observe on the telescope this week, which is going to be really fun. There are people who think about this, right? And I would say that there isn't really sort of one compelling model that does everything that you want it to, right? Like there are many different suggestions of models that involve exactly as you're suggesting, right? Different ways of taking all the different particles and sort of the energy that it takes to create those, right? That kind of energy is sort of permeating all of space, and there's not any single one of these that stands out is the correct answer. So a lot of what we're trying to actually measure is to try to measure the properties of dark energy and actually see if it really is true that the energy density remains constant, right? That idea is kind of consistent with this idea that there's just some kind of energy of space-time itself, and that could be related to all these different particles fluctuating in and out of existence. But again, I'm not really a theoretical expert on this, so I'm sorry I can't address it more specifically.
It's spread out.
Yeah. The idea is that it's basically spread out. Just like the air in this room is kind of spread out uniformly through the room. The idea is that this dark energy is, it fills all the space that's available to it. It's very smooth. Yep, in the red.
You said that there was more matter a billion years ago than is today. What happened to this matter?
Oh, I'm sorry. That may have been unclear. So what I meant is that, here, go back to this slide. Yeah. So what has happened is that this matter, right, which is the atoms in the dark matter, so the atoms in blue, the dark matter in green, that amount has actually stayed the same. What has happened is that as a fraction of all the stuff in the universe, it's become a smaller fraction of the amount of stuff in the universe, right? It's like the budget, right? The budget keeps on growing, and the fraction of the thing that whatever you're most interested in is shrinking at, by definition, right?
Conference always takes more money.
Other questions in the blue?
Last week we said that Einstein didn't know that the universe was expanding at an accelerating rate.
Right, that's true.
But you had a formula up there where you had like
Yeah.
like a placeholder or
this
something.
term right here.
Did he kind of feel that what we know now is dark energy, did he kind of feel that there must be something we now call?
Yeah, it's a really good question. So he realized mathematically that this was allowed. That there was no reason that you couldn't have this, right? in principle, the value of that, that lambda symbol, it could have been 0. And if its value had been 0, then there wouldn't be dark energy, right? But he had the insight to realize this possibility that it could happen. The same way that, gosh, I'm blanking on the name, but there was a Russian chemist who wrote down the periodic table, and he left gaps for atoms that hadn't been discovered yet, different types of elements, right? In many ways, Einstein had that same kind of insight where he realized that there was, that nature could allow this possibility, right? At the time, they didn't know, right? All they could see is that the universe was expanding, right? But he basically just realized that there was this possibility. It was actually, the measurement that the universe was expanding wasn't actually done until the 1920s. So when Einstein originally proposed this idea in 1915, that wasn't yet established. And so his original motivation was, if there isn't something like dark energy, right, then the attractive properties of gravity will eventually bring matter together. And so the universe over time would tend to collapse, right? It would tend to slow down and eventually turn around and collapse. And Einstein found this very unattractive theoretically. He was more interested in the universe that would keep on going for a long period of time. And so he originally proposed this as a way of saying, oh, well, maybe the universe is growing with time. Later on, he said, like, oh, I shouldn't have allowed my theoretical prejudices, to bias my mathematics. But then ultimately, right, he was vindicated, right? Ultimately, when it was realized that not only is the universe expanding, but it's expanding at an accelerating rate.
What year was that?
That wasn't, so there were hints of it as early as the 1980s. Do you remember when I showed this, yeah, so this is something, it's not something that a lot of people talk about as much, but it actually was. So even in the 1980s, people that were trying to understand how galaxies formed, right, they had a different motivation. They were trying to understand how did the galaxies form in the universe? And they were looking out and they were counting up the galaxies, and they kept on, finding this kind of inconsistency where their theoretical predictions were just saying there should be a lot more galaxies, right? Why aren't there more galaxies, right? Because they could do these simulations, right? They could just put the matter and the gravity into their computer, do the calculations, and they said, gosh, there really should be a lot more galaxies. What's going on, right? But then it wasn't until these supernova observations, in 1998 was when those papers were published, and then that showed this remarkable correspondence, right, between the theoretical models. The theoretical models that include the dark energy shown in black, and then their supernova observations. So then when they had this second line of evidence, all of a sudden everyone, you might think like this was such a shocking idea that people wouldn't have accepted it so rapidly, but the truth was that really this had been kind of brewing in the field for some time. Oftentimes when people tell this story, they want to make it sound very dramatic, like it was incredibly shocking. But within the cosmological community, there had kind of been hints of this. People kind of realized that something was amiss. And so when these dramatic observations came out, they were able to accept them and kind of change their thinking much more rapidly than if there hadn't been kind of these precursor notions. Yeah, in the red.
Back to your pie charts.
Yeah.
Two questions. One is on the today chart. Why don't you show the photons and neutrinos that
Good question.
are on the other chart? Second question is, if dark energy shares the pi with dark matter and baryonic matter, the atoms, and you rationalize that because energy and mass are equivalent,
Right.
why would you not have other forms of energy as part of that pi as well?
Exactly. Yeah. So the reason why we don't include the photons and the neutrinos is well, they actually are there, right? If you were to be proper, they should be there. But whereas I talked about how matter, its energy density right, becomes diluted by the same factor that the volume grows, it turns out that with relativistic particles, so particles moving very close to the speed of light, or at the speed of light in the case of photons, particles of light, it turns out that these get diluted even more, right? So the universe has grown by a factor of about 1,000, right, since this lower panel, right? So that means that the volume grew by a factor of 1,000 times 1,000 times 1,000, 1,000 cubed, right, for the three-dimensional volume, right? So that's by how much the matter was diluted, but the neutrinos and the photons, they were diluted by an additional factor of 1,000, right? And this additional factor of 1,000 comes because, just like we talked about the redshift, right, that these particles get shifted to longer wavelengths. So what happens is that, like, the effective pressure that these relativistic particles would have on, pushing, kind of causing the universe to expand, that's actually an additional factor of the expansion of the universe, that their energy is diluted, right? So they get diluted by a factor of 1,000 to the power 4, right? So they become 1,000 times less significant than the matter, like the atoms and the dark matter. And so by the time you get to today, it's an absolutely negligible fraction. It's much, much less than 1%. But if you were to be proper, right, I could have found a different graphic that showed this, it would have had those little snippers as well. Yeah, right behind, and the gentleman in black.
I was just wondering, does the fact that the universe has been expanding faster than people had anticipated for about 7 billion years, does that impact the calculations on the age of the universe, or the things that are further distances away?
Absolutely, yeah, that's a really great question. It absolutely has. It absolutely has. And again, this is another one of the one of the indicators that made people accept this idea more readily, is because there's different ways of measuring the age of the universe, right? Like one, probably maybe the simplest thing you can imagine doing is that you just look for the oldest stars, right? We know about how stars evolve over their lifetime, and so by looking at different types of stars, you can calculate their ages. And so what people were trying to do is that, without this idea of dark energy, it meant that the universe was a different age, and they couldn't get the ages of these oldest stars to match with the ages, that you would predict from, just going backwards in time, right? Because if it weren't for dark energy, yeah, that's this plot here. Right, so if it weren't for the dark energy, right, if you were to try to extrapolate backwards this rate of expansion, you just get the calculation wrong, exactly as you suggest, right? But once you include the dark energy, there's this kind of magic that happens where all of a sudden all the calculations begin to agree with each other. And, again, you can do this in many different ways. You can look at the abundance of hydrogen versus helium in the universe. That has to do with just the way that, different nuclei, different chemical reactions that occurred in the early universe. But again, there's many different ways of doing this, but once you include dark energy, they all line up. Yeah, White?
Is the acceleration going to continue to accelerate? And what does that mean for the universe, everything?
Yes, yeah, absolutely. Yeah. So I kind of left this open, this what next. So that's one of the reasons why we're so interested in measuring dark energy. I mean, we won't, it's on the scale of billions of years, so, who knows if we'll actually be around to witness this. But nevertheless, it's very interesting to, to wonder what might happen, right? And so, because there's this kind of runaway snowball effect where the dark energy becomes, a larger and larger fraction of the pie, its effect on the rate of expansion, what we would predict is that it's just going to keep on growing. It'll become, the typical distances between galaxies will continue to grow at a faster and faster rate. What that means, in kind of a practical sense, like if you take our Milky Way as an example, it doesn't mean that there won't be any more, galaxies around us. Actually, the nearest galaxy, Andromeda, or M31, as you prefer, it is actually on a collision course towards the Milky Way. So what happens is that locally, the attractive force of gravity can be enough that it overcomes this large-scale expansion, right? So And that's just because galaxies that are near to each other, that this attractive force between the matter is enough that it overcomes this dark energy. The dark energy really only becomes relevant if we skip ahead to here. Right? The dark energy becomes more and more relevant as you get further away. Right? As the scale of the universe is growing, the further you get away, the larger this amount of recession is. So if the galaxy is really near to each other, they can still overcome this. So what's going to happen is, a few billion years from now, Andromeda and the Milky Way will actually come together and form a larger galaxy, right? And there's a few other galaxies in our group that will come together, but the more distant galaxies, eventually they will recede away from us so fast that we'll just become decoupled from them. And they'll drift their own way, and we'll drift our own way, and eventually it'll become quite dark, right? We won't even be able to see very distant galaxies. Yes.
Following up on what you're saying, like currently, is there any way to actually delineate? Because there's the galaxies and then the clusters and then the superclusters.
Right.
And they're still being governed by the gravitational force as you just described.
Yep.
Is there any way to think about what the delineation is between that attractive gravitational force that is affecting the Milky Way and the expanse of the universe?
Yeah, exactly. So I'm just going to let this run in the background because it's relevant. So what happens is that usually the distinction that people make is that the clusters of galaxies, these are the largest structures, the largest amalgamations of galaxies, which are now decoupled from the so-called Hubble flow. So the Hubble flow refers to this large-scale expansion of the universe. Okay? And the clusters of galaxies, these are the largest structures that have, their collective gravitational attraction is enough that they decouple from this large-scale expansion and are able, they're mutually attracted to each other, and they will eventually collapse and form, their own structure, right? So that's usually the distinction that people make. When they talk about superclusters of galaxies, these are like the next bigger clusters of galaxies that haven't quite formed. They're like the clusters that might have been if there weren't dark energy, right? And why I wanted to show this simulation is that in this simulation, what's being done is that they've actually taken out the overall expansion of the universe. They're actually plotting the distribution of matter in coordinates that include this expansion, right? If you were to actually show this in terms of physical coordinates, right, what would be happening is the whole screen would have to grow, right? But what happens is that where you have these regions of matter over densities, right, they're able to come together despite this growing. But the more distant regions are kind of off, that would be off the screen, they're just getting further and further apart, right? So kind of the universe kind of like separates into all these, almost different like regions, like different watersheds, almost like you can imagine, separated by mountains. It's kind of the analogy, where the galaxies will flow together, but the neighboring regions will become separated. Yeah. Other questions?
What's causing the dark energy to remain constant as the universe expands?
That is the big question that we do not know the answer to.
Any ideas?
Yeah. So I mean, the simplest thing, right, is that there's just all these matter particles. Or sorry, forget I said that. The simplest thing is that there's this energy density of the vacuum that's corresponding to all these different types of particles flickering in and out of existence. It's kind of like an energy that corresponds to the potential of creation, if that makes sense. It's not something that we usually think about, but actually particles can kind of materialize out of space itself because there's this energy that that permeates all of space, and so it's possible to spontaneously create particles that flicker into existence for such a short amount of period of time that we can't directly observe them. But it allows the particles to interact with each other, right? It's a way, it's basically, these are called virtual particles, and it allows the different types of particles to interact with each other. These virtual particles, they're like mediators that allow the interactions to happen. And it's very mathematical, and I'm sorry if that analogy doesn't get you all the way
No, I was
there.
just,
But
as space expands, is there more of these virtual particles?
That's the idea,
basically?
is that this energy of potential creation, right? The idea is that this could be everywhere, permeating all of space. It's a property of the vacuum itself, so that even you take any region and you evacuate all the matter you could possibly think of, right? You make the purest vacuum that you could imagine, and even within that purest vacuum, there's still this energy of potential creation, right? The problem is that if you actually do that calculation, right? If you actually take all of our knowledge of particle physics, this like beautiful standard model, which makes precision predictions out to 12 decimal places, and there hasn't been any, like the standard model is probably the most successful physical model that we've ever come up with, right? The most precise, most powerful predictive theory that explains the most different diverse phenomena. But if you take that and you naively do the calculation of what this energy density should be, that's where you come up with this number that's so ridiculously too large, right? This where you get the number wrong by 120 zeros, right? So it's such a spectacular failure that it makes us feel like we're really missing something important, right?
But these numbers was because of experimentation or because of theory?
It's just theory.
Theory.
It's just theory, right? So like the standard model, right, has been tested extremely well with experiments like at the Large Hadron Collider at CERN in Switzerland. So in most respects, it's been this incredibly significant, important model for making sense of the universe. But in this one particular case, it just gets the answer spectacularly wrong, which makes us think that we're missing something important.
It was not because
Right.
the Casimir experiment or something.
You could also imagine doing that. I don't know the status of that experiment. I don't think that it's comparable to what we can do with our telescopes. Yeah.
What piece of this are you responsible for?
So I'm actually more interested in the dark matter personally, but I'm really interested in this experiment because it'll make more sense if I have a picture for this.
How did they come up with the constant number of 4 photons per cubic, whatever it was?
Cubic meter.
And can't you use that constant as a candle or a measure of the total?
Oh, that's what redshifting is.
Okay.
That's exactly what redshifting is. Yeah, so it's a critical part of the story. Yeah, that additional factor, right, just comes from the fact that as the universe is growing, the effective energy that you would measure, which is equivalent to the frequency of the particle, which is inversely proportional to the wavelength, right? That it becomes elongated as an effect of this expansion. Okay, so yeah, the part that I work on, I'm actually really interested in dark matter, and so this is taking a snapshot of one of those simulations where we've just allowed matter to evolve over time. Right? We've just taken matter and we allow gravity to do its work. And this is the distribution of matter that we would expect, right, in a system like the Milky Way. So, if you take a galaxy, right, and the size of the light that you would see from a galaxy is something like this, right? So what we imagine is that there's actually, because there's so much more dark matter in the universe than there is dark so much more dark matter in the universe than there is normal matter. What we imagine is that the galaxies that we see, they actually live inside these enormous clouds of dark matter that extend much beyond the extent of the stars.